Hello, let's continue our Sudoku adventure with Lil Overlaps by Randall. So this is a normal Sudoku plus some dots puzzle. So let's go over the rules. We have normal Sudoku rules, meaning in every row, every column, and every 2x3 box, we are placing the digits 1 to 6 exactly once each. We also have these circles in the grid. They're actually like brown diamonds with a circle in the middle. You take all the cells that it touches, and the digit is the sum of all of those cells. So all 4 of these sum to 12. These 2 sum to 8. So you can see how this only touches 2 cells, this touches 4 cells, these sum to 16. And that's it. Those are the rules. There's a link in the description if you'd like to try the puzzle yourself. And I'm going to get started right now. All right, so I think there's a lot of ways to think about these overlaps, but the way I want to present, which I think is going to be useful for other kinds of sum constraints you encounter, is that a box sums to 21 because it has the digits 1 to 6 exactly once each. If you add up 1 through 6, you get 21. And so what is the sum of 15 and 16? Well, that's 31. So that means that there's a difference of 10 between the sum of these dots, between these sum dots, if you take them together, and the box. We know the box is true. It's going to sum to 21. And so this overlap is the key. It means that the overlap is adding 10 to the total sum. Because if you think about it, the 16 is using these cells. Let's give that a color. And the 15 is using these cells. So these cells got double counted. So in order to account for the difference between 21 and 31, it's these 2 cells that got double counted. And they got double counted adding an extra 10. So the point is these 2 add to 10. There's only one way to add to 10 in a 6x6, which is 4 plus 6, unless you can repeat digits. There are cases where we could repeat digits, like here, but we can't within a box. So this is 4, 6. And now that adds to 10. That means this needs to add to 5, and this needs to add to 6. And I suspect there's only one way to resolve that. We aren't using a 4. So in order to add to 6 without a 4, we can't do 2 4, so we're going to do 1 5. Is it ironic that the 1 5 ended up being the 2 digits not part of the 15? That's kind of amusing. Anyway, and so then the 2 remaining digits are 2 3, which do add to 5. So 10 plus 5, 10 plus 6, it all works out. All right, now we need to get to 8, and we can't do 1 7 because 7 is not in the puzzle. So we need to do 5 3. All right, now we can do the same trick over here. So we know this adds to 21, but 12 plus 13 is 25, and so the difference is going to be 4. So this needs to be 1 3. We know the order because of that 1. This is 3 and 1. That's 2 and 3. So if that's 4, we might be able to figure these out as well. This needs to add to 8. We can't do 3 5. The 3 is already used, so we're going to do 2 6. And we know the order of that. That's 6, that's 2. That gives us 4 and 6 there. And then our final 2 digits are going to be 4 and 5, which go like that. And just to double check that I didn't mess up my math here, 9 plus 4 is 13. Nice. And then 8 plus 4 is 12. Cool. So all these sum dots work. Nice. Got the entire top band there done, along with a little bit extra. Now 16. I wonder if we can think about this. Or maybe the 8. Yeah, the 8 without a 5 is going to be 2 6. Okay, so now what we've done here, there's straightforward ways to see this. What we've done here is caused roping, and I want to talk about roping because we always have horizontal roping in 6x6, but we don't always have vertical roping. So if you notice the vertical roping, it often is helpful, especially if you notice it in a more holistic way. This is very straightforward, but if you have constraints that are kind of intersecting with the roping, it can be very helpful to recognize that it's roped. So what's happened here is the green cells are the same, right? 2 6 2 6. So we're going to talk about green as being 2 digits. And we're going to ask, where does green go in this box? Well, green ends up here. So I could center mark 2 6 here, and I will. And you can just see that. Where do 2 and 6 go in this box? Well, this 2 6 says not here. This 2 6 says not here. All right, but also now what I can do is I can just pick another color and call this 1 3 the purple. And this works even if we don't know what digits they are. We can just say these 2 are purple. Now, the question is, where does purple go in this box? Well, it can't go here, and these are green, which we know aren't purple, so purple goes here. So this is the 1 3, and we know the order. And then where does purple go in this box? It goes here. So this is 1 3. And then finally, we can call this blue. I mean, obviously the color doesn't matter. And so then the blue goes here, and the blue goes here, and these are 4 5. So the roping is if you get just 2 vertical set pairs of digits, that exactly match, the 2, 6 and the 2, 6, that's enough to force this entire pattern where you end up with repeated digits vertically the entire time. We have not proven that's the case here. If this could be something other than 2. If this ends up a 2, then this is also vertically roped. If this ends up anything other than 2, then we are not vertically roped. We're forced to not be roped, which means that we'd have different pairs of digits in each vertical. All right, cool. So we don't need that coloring anymore. So 16, this is 3. So these 3 need to add to 13. Do I know much about that? Well, that's pretty high because this maxes out at 5. So let's talk about minimums here. What's the minimum these 2 can add to? If this was 5, so we want to maximize the other 2. So this would add to 8. So at minimum, this adds to 8. So this adds to 8 or 9. If this added to 8, we can't do 3, 5. So we'd have to do, well, we can't do 3, 5 or 2, 6. So we can't actually add to 8. So we have to add to a 9. We can't do 3, 6. We do 4, 5. So this ends up being a 4, 5 pair here. And then this has to be 4 because 9 plus 3 is 12. We need 4 more for that. So that's 4, 5, and 4. Nice. Resolves all of these. And then now we should just be Sudoku. So this column needs a 1. There's the 1. This is a 6. That gets us 2 and 6. The 1 gives us the 3 and the 1. We do it in the corner. Very nice. This is a, oops, not a 3. I misscanned. This is a 5. Over here we need a 1 and a 2. There we go. Down here we need a 4. That goes there. This needs to be a 2 or a 6, but it can't be 6. So that's 2, 6, and 2. Up here we need 3 and 6. We go in that order and we're done. Very nice. All right, so thanks, Randall. That was a neat use of some dots. We did end up roped over here as well, which I didn't notice. At some point, we placed that 2 there, forced it. But I was just finishing up the puzzle, I guess. So yeah, we were vertically roped. Again, it's not forced to happen. The horizontal roping in 6x6 is forced to happen, and 9x9 roping can happen, but is not forced ever. In 6x6, you always are roped with this triple appearing here, this triple appearing here. It's pretty easy to just notice that would be the case. Vertically, though, you do need to prove that it's roped before you can use it, and it's not always roped. Cool. Well, hope you enjoyed this. And if you did, then why not leave a like, subscribe, and a kind comment below.